Okay, let's unpack this. Today we're going really wide. Think billions of miles wide, starting with how planets are born, maybe even how life gets started, and then landing right back here on Earth. We're looking at ancient Roman armies, their movements, and even, well, the architecture of power today.
Yeah, it sounds like a huge leap, but there's a connection. We're looking at sources, new research, archaeological finds, and what ties it all together is how this new evidence keeps forcing us to rethink things we thought were, well, settled, whether that's planet formation or historical record.
Exactly. Assumptions getting challenged left and right. So let's start way out there. The habitable zone, the Goldilocks zone.
Yeah.
We all learned it's about temperature, right? Where water won't freeze or boil. Simple enough.
Simple, but maybe too simple, especially when you look at the most common stars out there, M-type stars, red dwarfs. They make up maybe, 75% of the stars in the galaxy?
A huge majority.
Right. But they're small, they're dim, so their habitable zone where liquid water could exist temperature-wise, it's really narrow, and it's incredibly close to the star itself.
And close means trouble, usually.
That's the thing, yeah.
Yeah.
Being close means you're getting blasted. The temperature might be right, but these red dwarfs, they throw off these massive flares, huge bursts of X-ray and UV radiation, XUV radiation.
And it's not just a little extra radiation, is it? I saw the numbers from the Galax data. Staggering.
Oh, completely. The far UV radiation from these flares, on average, it's 3 times more energetic than we used to assume. And sometimes it spikes to 12 times what models predicted.
12 times. I mean, 3 times is already like moving from Alaska to Hawaii in terms of sun intensity, right? That's the comparison I read.
Exactly. And that constant, intense back of XUV, it does something pretty destructive. It causes what's called hydrodynamic atmospheric escape.
Basically boiling off the air.
Sort of, yeah. It heats the upper atmosphere so much that it just expands outwards and gets stripped away by the stellar wind over time. So you could have a planet in the perfect temperature zone, but it just loses its atmosphere, becomes barren.
So red dwarf habitable zones might be a bit of a death trap.
Sure.
But hang on, there was a twist, wasn't there? A kind of double-edged sword.
There was, and it's fascinating, that same high-energy UV radiation, the stuff that destroys atmospheres, it might also be necessary, or at least helpful, for creating the building blocks of life.
How does that work?
Well, the thinking is that this UV energy could help drive the chemical reactions needed to form things like RNA molecules, the very components you need for life to get started. So the thing that kills could also be the thing that creates.
Wow. So it's life on a knife's edge, potentially.
So precisely. It's a real paradox.
And there's a specific star system where this is being modeled, right?
Yeah.
AU Mike.
Yes, AU Mike. It's a young star, and it has this Earth-sized planet, AU Mike D, orbiting near the outer edge of its habitable zone. The models show that, without the flares, its atmosphere would probably be fine, stable for billions of years.
But with the flares.
With the extra XUV energy from those flares included in the model, that's the only thing that really drives significant atmospheric loss. It basically proves that for these planets, just being the right distance isn't enough. The star's temperament is critical.
So habitability is way more complicated than just location, location, location.
Definitely. The environment matters hugely.
Okay, so that's how planets might live or die. Let's talk about how they form, specifically the big ones, the gas giants. Because it sounds like the textbooks might need a serious rewrite there, too.
Oh, absolutely. Here's where it gets really interesting, as you say. For decades, planetary science has had this kind of debate going. 2 main ideas on how you build a Jupiter.
Right, you had core accretion, which was always the favorite, wasn't it? The slow and steady model.
Exactly. Bottom up. Dust clumps together, makes pebbles, pebbles make rocks, rocks make bigger rocks. Eventually, you get a core maybe 10 times the mass of Earth. And then once it's big enough, it starts pulling in all the hydrogen and helium gas around. It takes millions of years. It's, orderly.
Felt logical.
Yeah.
But then there's the other idea, gravitational instability. Much faster.
Much faster and much more chaotic, top down. This idea says that sometimes huge chunks of the gas and dust disk around a young star just collapse directly under their own gravity. Boom! You get a giant planet, maybe in just hundreds or thousands of years, not millions.
And the problem for the slow model, core accretion, has always been systems like AB Aurigae.
That's the poster child, yeah. ABRD is young, like really young, maybe 4 million years old.
Yeah.
But it already has a planet forming that's 9 times the mass of Jupiter.
Way too fast for core accretion. You just can't build a core and then grab all that gas in only 4 million years.
Exactly. That speed was the big sticking point. Theoretically, gravitational instability could do it, but, seeing is believing.
And now we've seen it with the ALMA telescope.
True enough, yeah. Researchers used LMA to look not just at the disk around AB Orgy, but at how the gas inside the disk is moving, specifically within the spiral arms.
And they found something specific, the hallmark signature.
That's what they called it. They detected these distinctive wiggles in the velocity of the gas, little variations in speed. And these wiggles, they match exactly what computer simulations of gravitational instability predicted should happen.
Wow. So not just a theory anymore, actual observational proof.
It's huge. It means this rapid top-down way of forming gas giants is real. It happens. And maybe it's even common.
Okay, hold on. If gas giants can form that quickly, like almost instantly in cosmic terms, what does that do to the rest of the system? Doesn't a giant planet forming fast mess things up for smaller rocky planets trying to form nearby? Like, does it steal all the material or kick them out?
That's the million-dollar question, isn't it? If this rapid formation is common, it totally changes the timeline. Maybe terrestrial planets don't have as long to form as we thought in some systems, or maybe the conditions for habitability arise much, much sooner in a system's life than our old model suggested. We might need to look at younger stars.
Younger stars.
Okay.
Speaking of weird planetary setups, let's talk about some of these anomalous exoplanet architectures, specifically eccentric warm Jupiters.
Right. So these are gas giants, bigger than Jupiter, but they're not super close. Hot Jupiters. They're warm, and their orbits aren't nice circles. They're really stretched out, eccentric, oval-shaped.
Okay, so what's the anomaly?
The weird part is their alignment. Hot Jupiters, their orbits are tilted all over the place compared to their star's equator. Random. But these warm Jupiters, they're almost all aligned with their star's equator. And here's the real kicker. The more eccentric the orbit is, the more stretched out and weird it is, the more aligned it tends to be with the star.
Wait, that seems totally backward. Wouldn't a really wild eccentric orbit be more likely to get knocked out of alignment over time?
You'd think so. That's why it's anomalous. It defies the standard models of how planets migrate and settle into orbits. Nobody has a perfect explanation yet.
What are the leading ideas? How could that happen?
Well, there are a few. Maybe there are other unseen planets in the system pulling on it in just the right way. Maybe there were some really complex interactions with the gas disk early on that we don't understand. Or the really exotic idea is something inside the star itself, like internal waves somehow interacting with the planet's gravity, pulling energy out of its orbit and forcing it into alignment as it gets more eccentric. Still very much a puzzle.
Weird orbital mechanics. But sometimes stability can arise in really complex places too, right? Like the TOI 2267 system.
TOI 2267. Yeah, that's a fantastic example. It's a binary system, 2 stars orbiting each other, and they're M dwarfs, small and dim, M5V and M6V orbiting closely.
And the big deal is planets orbiting both stars.
Well, planets orbiting the primary star, but potentially stable in this binary environment. And they're Earth-size. That's what's so significant. It's the first system found that might have transiting Earth-sized planets confirmed orbiting one star in such a tight binary.
So small rocky worlds surviving in a 2-star system. How do they manage that?
We know about 2 confirmed planets, TOI 2267b and c. They're about 0.95 and 1.13 times Earth's radius, so definitely Earth-size. And the key to their survival seems to be resonance. They're locked in a stable 3:2 mean motion resonance, or MMR.
Meaning?
For every 3 times the inner planet B orbits the star, the outer planet C orbits exactly twice. It's like gears meshing. This rhythmic gravitational interaction keeps their orbits stable, preventing them from interfering with each other catastrophically.
And that suggests how they formed.
Yeah, it strongly suggests they migrated inwards through the early disk and got caught in this resonance. It's called resonant capture. It shows that even in these really dynamic binary star environments, stable planetary systems, even with Earth-sized worlds, can actually form and survive.
Amazing. That idea of architecture, of structure and stability. It's a great point to pivot, actually. We've been talking about the structure of planetary systems billions of miles away. Let's bring it home. Let's talk about the architecture of human history, power, conflict, right here on Earth.
Good transition. And we can start with something incredibly tangible. The Bunnik coin hoard found in the Netherlands.
Right, this is amazing. A pot of coins, basically. 404 gold and silver coins, buried about 2,000 years ago.
And the context is really specific. The dating, based on the newest coins in the hoard minted under Emperor Claudius, puts the burial right around 43 CE.
Which is exactly when Rome invaded Britain.
Precisely. And the mix of coins tells a story. You've got 44 British gold staters, probably loot, or maybe tribute paid by local kings like Cunoblinus. Then you have 72 Roman gold auri, and, significantly, 288 Roman silver denarii. The denarius was like the basic pay unit for a Roman soldier. This was serious money. A soldier's life savings, maybe, or part of a unit's pay chest.
So it connects directly to that military campaign. But the sources said this find was unique. The first physical evidence of something specific.
Yes. It's described as the first physical proof found on the European mainland showing troops actually returning from the invasion of Britain. You can almost trace the journey soldiers paid in Britain, carrying their wages and spoils back across the North Sea, and then, for whatever reason, someone buried this stash near Bunnik.
Wow. That physical link back. And there was one odd coin in there too, wasn't there? That told an even bigger story.
Ah, yes. The single Numidian denarius. A silver coin from North Africa, mixed in with all the British and Roman coins.
Why is one coin from Africa in a Roman soldier's stash buried in the Netherlands so important?
Because it shows the reach of the Roman military machine and the life of a soldier. Whoever buried this hoard had likely served in, or at least interacted heavily with troops from the North African provinces before being deployed to Britain. It connects that spot in the Netherlands not just to Britain, but across the Mediterranean to Africa. One coin mapping out a soldier's career across the empire. It speaks volumes about movement, logistics, conflict.
A tiny piece of metal telling a huge story about the architecture of an empire.
Exactly, the physical traces left behind. Which, in a way, brings us to a much more recent example of, let's say, architectural statements and power. The recent renovations at the White House in Washington, D.C.
Right. The sources detail some significant changes under President Trump, starting with that executive order about classical architecture.
Yeah, a mandate essentially saying new federal buildings should look, well, classical. A very specific aesthetic choice reflecting a certain view of heritage and government style.
And then the physical changes to the White House itself. Funded by private donations, wasn't it? Around $250 million.
That's the reported figure, yeah. And the changes were pretty symbolic. Things like covering walls and some furniture in the Oval Office with actual gold leaf.
A very direct visual statement.
Unmistakably. And structural changes too, the demolition of the East Wing, and probably most talked about, replacing the Rose Garden's lawn with a concrete floor.
What was the reasoning given for the Rose Garden change?
The stated reasons involved accessibility and preventing issues like high heels sinking into the grass during events.
Okay. And there were other actions mentioned around the complex too, more symbolic ones?
Yes, the sources noted the attempt to remove the long-standing peace vigil outside the White House fence. The anti-nuclear protest that's been there continuously since 1981, they cleared it, but the demonstrators rebuilt it quickly. Still, the act of trying to remove it was seen by many as symbolically significant, reshaping not just the physical space, but the cultural landscape around it.
So, okay, what does this all mean? We've gone from the high-energy radiation zones around red dwarfs to maybe seeing gas giants form in thousands, not millions of years, analyzing these bizarrely aligned warm Jupiters, seeing stable Earth-sized worlds orbiting binary stars, then jump to a Roman soldier's pay, buried in the Netherlands, with a coin linking him to Africa, and ended up discussing gold leaf and concrete in the White House complex.
It seems disconnected, but the thread is that our understanding is always being updated by new evidence, often unexpected evidence. It's the anomalies, the Numidian coin, the wiggles in the gas disk, the weird alignment of those planets that push science and history forward. It shows that the neat models we have are often just, well, approximations of a much messier reality.
Our assumptions are constantly being tested, whether we're looking at stars or stones.
Exactly. Nothing is ever completely settled.
Yeah. Which leads to a final thought. Building on that planet formation discovery. If that top-down, super-fast gravitational instability model is more common, if gas giants can really form in just, say, 10,000 years instead of 10 million, what does that do to our assumptions about how long it takes for life to potentially get started? If the system settles down much faster, should we be looking for signs of life, maybe even complex life, around stars and planets that are much, much younger than we ever thought possible? That's something for you to think about this week.